Hello and welcome to Dare to Know, interviews with quality and reliability thought leaders. I'm Tim Rogers, and today I'm pleased to welcome Anne Meixner. Anne is the principal owner of the Engineers Daughter LLC, where she provides consulting on semiconductor test manufacturing and design for test. She has over 30 years of experience as an engineer and technical leader, including more than 20 years as a test technologist at Intel in Hillsboro, Oregon, focusing on mixed signal and analog test methods. While at Intel, she applied new test technologies to ease manufacturing test cost while maintaining or improving test coverage. Anne received her PhD in electrical and computer engineering from Carnegie Mellon University, where she studied fault modeling for analog circuits. Anne, it's great to have you with us today. Welcome, and thanks so much.
I'm delighted to be here.
And it seems like we're always hearing that we live in a digital world. Why are analog and mixed signal devices still important?
Because the claim that we live in a digital world is false. Uh-huh. We consume content, we work in a digital world, but the world we interact with every day is physical. You touch things, you feel things. Temperature is an analog parameter. It is not a digital parameter. We transform the analog world into digital information that can then be processed. Right? Electronics started off being analog, and digital really came about in the 60s after the transistor was born in the late 40s, but it took a while to figure out how to really use that, right? So, and even transistors of themselves, we're also saying they have analog functions as well as digital functions, the primary way we use that. Another sort of different tact on that is, well, people think about digital circuits as, hey, these are just these ones and zeros and it's just digital in nature. If you contemplate or think about how the rates, the clock rates, and how fast data is going through those digital circuits, we don't have square waves anymore. They're kind of more like sine waves. When you go at 1 gigahertz or 1 gigatransfer per second, you're talking about things in terms of nanoseconds.
Right.
So there's two ways to play that. One, just in designing digital circuitry for high-end performance computing, you really have to take you have to take into account a lot of the analog parameters. From a integrated circuit point of view, what's happened over the decades, or what people started seeing as you had integration of both digital and analog circuitry, either on the same integrated circuit that's a piece of silicon, or in a heterogeneous sort of package where you may have something analog and digital on the same package communicating to one another on a package instead of a board, is you have this mixed signal design that you need to take input from the real world, translate it into digital format to be computationally churned and used and information transmitted.
Sure.
Everyone owns a car.
Uh-huh.
Are cars digital?
Well, that's a good question. It seems like they're getting more and more digital all the time.
Well, there's more and more electronics on there. I mean, there've been electronics on there for decades, but it's become more and more. There's more control of functions, fuel injection, as well as integration with smartphones and communication with satellites, et cetera, right? But you don't measure a temperature with, a digital circuit. You measure temperature with an analog circuit and then translate that too.
Yep.
Pressure sensors for cars, right? My car will tell me, hey, one of your tires is low. Go check that out, right?
Right.
There was a physical sensor in there that somehow had to get transmitted, and then someone had to program the software, say, if this changes to this, send off this warning light when the car starts up next time.
Right. And I wonder if you could tell us a little bit more about your work assessing analog fault coverage and ensuring adequate coverage. I guess what I'm particularly interested in is what some of the mistakes are that designers and test engineers make when they're developing a test plan.
All right, I'm going to answer this in two parts. First, I'm going to kind of give the arc of what's happened in the last 30 years here. When I started off my PhD work, that's when people were started worrying about mixed signal. And I was like, okay, well, how do we assess the college? And I looked, hey, digital circuitries have digital fault models to assess coverage. We don't have anything for analog. How would I go about building a fault model?
Good point.
And a model is a behavior. A fault model is a behavior where you can say, when it's faulty, this is the behavior I'm going to see. And then when it's not faulty, I'm going to see a different behavior. It's tied to how you test it.
Right.
So digital fault models started off being, I'm stuck at 1, I'm stuck at 0. But as Moore's law progressed and data rates started going faster, people snuck in. That wasn't enough. You had to worry about delays. You had to worry about transition-related faults.
Mm-hmm.
You had to start worrying about, well, it may be what the nearest neighbor is doing, so let me test the fault multiple times. I may see slightly different behavior.
Right.
But it's tied to how you test. Fundamentally, stuck-at fault modeling for digital was supposed to on voltage. With CMOS, people started saying, hey, I can measure current in the power supply and tell if fault's happening, because CMOS is supposed to be statically, there's supposed to be no current draw, right? So therefore, you've changed the test, the fault model in a sense, and how you test it. So the challenge when I did the analog fault stuff, I was hanging out with analog circuitry hammers. You have to worry about parameters. There's so many parameters and all that. And the biggest learning I got from doing my work is understanding that a fault model is tied to how you test it. Now, what's adequate coverage? A fault occurs because you have a defect, a change in how the circuit was manufactured. It can be something structural, like I have a short between 2 nodes. It can be I have an open. But it could also be, hey, I have a shift in process, or I have a mix match.
Right.
One of the things when analog circuit designers are paranoid about process variation and process shifts. And so there's a lot of effort gone into either through the design in terms of physical layout to mitigate those impacts, as well as compensate for it. Hey, if I want to go at 5 gigatransfers per second for PCI Express, my diff amp for the input receiver has got to have really, really small gates because I want to keep the capacitance low. If you have really, really small gates, you have big variation in threshold voltage, which translates into offset. Oh, I'll add all this other circuitry to compensate for that because the speed's important. So those trade-offs are made. So when I did my original PhD work, I just focused on shorts. Mm-hmm. I dabbled in opens. I just worked on the shorts and didn't worry about process variation, because sometimes you say you walk before you run.
Sure.
You know, when you're starting off in a new area, you don't. The other thing is, hey, the process stuff, it should be okay. And so how do you assure adequate coverage it's not just about, I'm talking about coverage in terms of a defect-based approach. And the motivation to do that happened with digital a long time ago. It's now, it's been happening with analog. People are starting to look up it. No one's had, hey, what's the metric to do that? And fault models, in the end, probably aren't the way to go. We're talking about defect coverage. If I have a short, can I detect it with some of my tests? Got it. Analog historically has been tested with very specification-oriented tests. This is the 3D build point. This is the maximum offset. Uh-huh. This is the slew rate. But those can be very time consuming. And while you have say you have an up amp from Texas Instruments that you have to test, if you have multiple up amps providing functionality for mixed signal circuits on your integrated circuit, you can't test each up amp with that level of degree. So then what do you have to test for? Right. I am participating in an IEEE working group that's focused on coming up with a standard for analog test coverage or sort of defect coverage.
Got it.
And that standard, we're having those discussions about structural versus how much parameter. And the direction we're trying to take is within the normal process window or variation the designer designs for, we're not worried about that. It would have to be something bigger than that. I want to go look up, I didn't tell the name of the standard of the study group. It is IEEE P2427.
Uh-huh.
So we're working on a proposal for our standard on this, and we were just officially sanctioned a couple weeks ago.
Outstanding.
Yeah. And I'm getting to work with people that I've known for years. And I'm very excited because this is a topic that's near and dear to my heart.
Obviously.
Now, to get to the part, what are the mistakes? So that's sort of the coverage. Like we've gone through, there are 20 or 30 years, and I will be, when I'm going to be starting up the Testing 123 blog again, and I can address some of these topics in greater depth there. You asked about, hey, what do designers or test engineers, what kind of mistakes do they make when they're trying to figure out how to test, say, a mixed signal on a device?
Yeah.
And it's designers and test engineers will have slightly different perspective. In my work with designers for high-speed I/Os, things like PCI Express and USB, sometimes they just were ignorant of the test methods or the test environment. For instance, as the data rates increased, they had to start adding equalization to either the transmitter or receiver. And you could turn that on and off. And I said, well, I'll turn it off. And if then it won't work and I'll know. And I was like, wow, the problem is you've designed that equalization for a particular system with a particular transmission line. We're going to have a different transmission line in our test.
Wow.
So they tend to take a spec oriented, like, well, if I don't have it on, it won't work.
Right.
I'm like, well, you're not. So part of it, it's understanding, hey, here's a test. And not all designers are like that, but I ran into that sometimes. Like, wow, or I just need to do this. It's like, well, you're not necessarily, thinking about there are differences in a test and a manufacturing test environment and mission mode.
Good point.
The good part is because of what I mentioned earlier about analog designers and all that compensation circuitry, we were often able to use that compensation circuitry to help us do the testing. We would work with designers to say, can we get this range a little bit longer so we can actually do the testing? Because we might need the difference in how you use something to get the job done in mission mode is different than when you try to use it as a ruler.
Sure.
Now, for test engineers, when they're developing a test plan, this gets back to how do you have enough test coverage? And that's why I think the IEEE study group for this standard is so important, because we haven't had anything to help adequately, measure so you could check one method versus the other.
Right.
So the challenge has been, how do you assess, I got, say, 20 seconds to test all this circuitry. How do I know? How do I choose behind a myriad of tests and balancing off the test time? For test engineers, there's often the balance of, I only have so much time, but I also have to get everything.
That's not much of a budget to work with.
Well, I'm throwing a number out there as a sort of straw,
Sure.
Straw number there. But just to demonstrate, there's a fixed time they have to do. And often when you start up a product in production, you may have a longer test time actually to help you gather data. Is anything failing this test, right? If you take spec test, if something never fails, why are you testing it?
Good
right?
point.
There should be the test in there should be there to help you discern, is this a product I shipped customer or not? If you have so much margin to design, this is never going to fail, that test has no value.
I agree.
And in this case, it's about, this is where the, test engineering is focused on quality at time zero.
Right. That's a good way to put it. And in one of my early jobs, I worked on a design for manufacturability project. And this whole idea of design for, DFX has always been very interesting to me. I wonder if you could comment a little bit on the role of a test technologist in a design for reliability program. Or I guess another way to put that is, how does DFR change test design?
I've only just been starting to think about this. I attended both ISTFA, which is for failure analysis labs, last fall, and I just came back from RAMS. So I could understand a little bit more, well, what are the concerns and stuff? Because I've always had a very quality focus, so at Intel, it was the Q and R, and I usually mostly worked with the Q. The only thing I knew about the R was, hey, we have this thing called burn-in that we have to do, and it's there for reliability. So here's what I've come to, I'm beginning to appreciate parts of about the reliability is, all stuff eventually has wear out.
Right.
Electronics tends to not wear out as quickly, but you can have defects that are latent that will manifest itself later due to electromigration, pin ox hole, and things like that.
Right.
As I think about it, one aspect for design reliability is to know, hey, has this failed out in the field? Mm-hmm. And often with our DFT methods, we have what we call built-in self-test, that you have the ability to test out in the field, hey, is something failure? In fact, for automotive, because of all the emphasis on a new, I think it's ISO 6262, it's for automotive safety, functional safety, that they're requiring, if you are in a certain criticality part in the automotive, you need to be applying tests on a regular basis, right? So there's a potential, right? That means they have to be kind of self-test. They can't necessarily be having a piece of equipment attached to it.
Right.
So there's an opportunity to say, has something changed, and get an idea really what the lifetime may be for a part and get a part there. So one, DFT can play a role in terms of just gathering data to find out, hey, when did this fail? In terms of test methods, trying to detect things that reliability failures at time zero is something to focus on. And often that actually ends up being usually more analog in nature than digital. I remember an engineer that I worked with, he did this work on there were some contact resistance issues happening that would explode into a defect. There was a reliability failure later. When he went back, he said, well, if we can measure the contact, this resistance level or this voltage level to a finer degree than we need to, we can screen these out early, right? So that's how a test method can help, do that. That's not necessarily a design for part. The other thing in terms of design reliability, if things fail, can you recover?
Sure.
Do you have any resilience built in or redundancy built in, right? So an excellent example are embedded memories, whether they're a static memory or maybe even embedded DRAM. But there's a lot of redundancies have been in there, even just to help with time zero to recover for yield recovery. But even out in the field, you can run a test and suppose there's, if something does fail, do you have a spare part to put in there? Things like high-speed IOs are often in multiple lanes. And if there's a failure, it's architected often to keep going at half the bandwidth. And then a flag sent out, hey, go change out this card. That's important in server-based applications like financial transactions, airplane reservations, and putting there. So the performance may go down, but you're not losing connectivity. And so while that's not necessarily mean, you could call that a design for reliability feature. From a test point of view, anytime you add in features that are going to be used in the system for some sort of system mode, you want to make sure they're working correctly at time zero so that when you do rely upon them, they're going to be working.
Sure.
Right? An untested circuit is bound to have a defect.
I think that's a version of Murphy's Law, isn't it?
I think I recently read about Murphy. I think he was an aerospace engineer in NASA or something, and he's much misaligned. I hope to write an article on him sometime. He was like, you need to prepare for the worst.
Yeah.
Because in NASA, people's lives are at stake, right? You have, and I think it was partly a result of some of the early missions where astronauts did die, right? And so it was in general, like, if something can go wrong, it will. Let's prepare for it and not like be unprepared. And so it's a part there.
And in the time we've got left, I'd like to ask you about a couple of other things. You've been involved in providing some career development support for engineers, and I wonder if you could share a little bit about some of your activities on that.
Well, thanks for asking about that. It's one of the things that when I decided to go into self-employment, I looked at my skills and what I did at Intel, and I said, one of the things that I did was help nurture the next generation. How do you do that as a self-employed person, right? You don't have anybody on your team. But I really wanted to continue that because I really enjoyed it. And I looked around and said, hey, some people are doing this thing called engineer coaching. Well, let me kind of listen in and understand what they're doing. Let me go read some books, about sort of those transitions. Let me think about my own career and how things change. And so in the past 2 years, I've been giving talks. I developed a talk for Global Tech Women's Their Voices Conference in 2017 called Demystifying the Corporate Technical Ladder. Uh-huh. And as part of that, I went and interviewed several other technical leaders, people I knew at Intel and some people who I knew who weren't at Intel, so that it wouldn't be just my experience that was informing, hey, what I was sharing there. And so sharing that, hey, here's this. What's the difference between a business manager and a technical leader? Because there's a lot of overlap in leadership skills, but what's the difference? And so could share other people's, hey, what's the common struggle everyone has? What are the 4 areas that you're assessed as you try to go up a corporate technical ladder? What do you need to be doing? What kind of conversations do you have with your manager? Right. So I have a talk and I had, hey, here's a little 1-page development to help guide you on that.
Wow. That's great.
I have a big passion for helping people present their technical ideas. So I have a talk this year at Global Tech Women called Getting to Present. What's the process from where do you want to present your brilliant idea to, the actual day of giving a presentation? There's a lot of steps in between. It's not just, hey, here's how to give a talk. No, you have to think, where are you going to go? What's the process? And trying to treat this as, hey, this is a journey. I've often given feedback on people's written stuff. Even people like of my age is like, hey, do you want some feedback? Sure, I'll give you some feedback. And I'm the type who will give lots of feedback. And they're like, oh, this is good. Eventually I'll get paid for that. And so as part of that, I was approached by someone developing professional development for Society of Women Engineers. Hey, could you come in and help us do something about technical presentations? Uh-huh. And so I was already thinking about it from a formal paper point of view. So I took some of that, but I created a new presentation that I called, something like, what is it? Presenting technical content with confidence. Where it's focused on internal work presentations. And I tried to do sort of a hands-on component, and I got some good feedback. And so I actually submitted that to Society of Women Engineers, now having these local events. And there was one in Portland happening in April. So I submitted a bunch of ideas for talks, actually the 3 I've just talked about. and 2 of them got accepted. One, the technical confidence and that. And I attend the PDX Women in Technology. I attend their networking events, and just informally, I talk to people like, oh, hey, so-and-so knows me here. Let me introduce you. I mean, just connecting people,
Right.
suggesting resources. I have coached one individual engineer. I would enjoy doing more, helping them with something that they're dealing with in their career or helping with their career growth. And I plan to start writing about some of the sort of technical communication aspects and sort of pop some of those into Testing 123 blog.
Right.
So that's what I got there.
In the time we got left, I also want to ask you a little bit about your oral history project. If I understand correctly, you've been collecting stories from engineers. What's the current status of that?
Well, I'm glad you asked about that because actually the Engineers Daughter blog site was actually where I spent a lot of my energy when I first left Intel. I had this idea. I want to share engineering stories. How do I do that? Blog. And I basically started off with, I'm going to share my own stories. And it kind of, the actual title, Engineers Daughter, the apostrophes after the S, is in tribute to my parents, who both were engineers. My dad from all of his career, my mom sort of in an industrial engineering capacity in the late 50s, early 60s. So, I grew up in an engineering culture. So to me, I benefited from that. I also benefited from many engineers that I worked with when I was a young engineer, right? Things that they told me, wisdom that they shared. How do you contribute that? And a story is such a better illustration of that than just saying Murphy's Law. Right. So nothing against Mr. Murphy.
No, you're right.
And I'm actually now in the process. I have started collecting other people's stories. We're getting ready to start publishing those. What we found out is that people are too busy to write. And writing, as I know from all the training that I give people, writing is a lot of work and it's revisions and stuff.
Sure.
So what was suggested to me is, but you could talk to them and they tell you the story. And I went, And then it went, well, not only that, engineers gather at conferences. You could provide this as a service to conferences and collect your content and be paid to do that. So we're exploring doing that. We are, we did a pilot for free at a local conference in Portland in the fall. And I'm, haven't gotten to those yet, but I also interviewed 3 different engineers and got some of their audio that are in the process of being transcribed and converted into stories. Sometimes 20 minutes of talking to someone, there may be a 5-minute story there.
Right.
And I'm very passionate about this. I think it brings the focus on the stories is the craftsmanship side of engineering that doesn't get talked about enough, and in a sense, kind of gives a human side to how do you go build the Brooklyn Bridge? Even a rivet, how it's built, how it's designed, that can be a very enthralling story if told right.
Good point. Well, I think this is great work. I'm very impressed with this project. I'm looking forward to hearing more about it. And thanks so much for joining us today.
I was delighted to be asked to share my thoughts on testing and quality of electronics, and as well as some of the other work I'm doing to promote engineers.
Great. Thanks. That was Anne Meixner, consultant and principal owner at the Engineers Daughter LLC. For more information about Anne's work, go to AnneMeixner.com. That's AnneMeixner.com. And to learn more about her oral history project, go to www.engineersdaughter, that's all one word, engineersdaughter.org. This is Tim Rogers. Thanks very much for joining us.